Revolutionizing space travel, Rosatom's new plasma electric rocket engine promises Mars mission in 60 days. Date: February 10, 2025. In a groundbreaking development that could change the landscape of interplanetary travel, Russian scientists from Rosatom have unveiled an innovative prototype of a plasma electric rocket engine. This new propulsion system is designed to significantly reduce the time required to reach Mars, potentially achieving the journey in as little as 30 to 60 days. This represents a major advancement compared to traditional rocket engines, which typically take nearly a year for a one-way trip to the Red Planet. 1. Technology Overview. The newly developed plasma engine is based on a magnetic plasma accelerator. Diverging from the traditional fuel combustion methods that have dominated space travel. The engine operates using two electrodes to create a magnetic field that accelerates charged particles, specifically electrons and protons, at remarkable speeds of up to 100 km per second, approximately 62 miles per second. With an average power output of around 300 kilowatts and a thrust of approximately 6, and this engine surpasses many existing propulsion systems in terms of performance. 2. Safety and efficiency. One of the most significant advantages of this plasma propulsion system is its potential to enhance astronaut safety during interplanetary missions. By drastically shortening the duration of space travel to Mars, the risks associated with prolonged exposure to cosmic radiation are minimized. This advancement could make it feasible to send astronauts to Mars and back safely, addressing a key concern in human space exploration. 3. Testing and development timeline. Currently, Rosatom is assembling a large-scale experimental setup to conduct rigorous tests on the prototype. This facility includes a 14-meter-long and 4-meter diameter vacuum chamber that simulates outer space conditions. The immediate focus is on refining the engine's operational modes, with a flight-ready model anticipated by 2030 following extensive ground testing. 4. Launch mechanism. While the plasma engine will provide propulsion for the spacecraft once it reaches orbit, the initial launch will still depend on traditional chemical rockets. This hybrid approach allows for a smoother transition from Earth to space, where the advanced plasma technology can be employed for deeper space missions. 5. Increased scope of exploration. The implications of this revolutionary technology extend beyond just Mars missions. The potential for faster travel to other planets, and even beyond the solar system, opens up exciting possibilities for interplanetary exploration. This development could pave the way for future missions to destinations previously considered too distant or challenging. 6. Comparison with other initiatives. As Rosatom advances its plasma engine technology, other countries, including members of the European Space Agency and the United States, are also investing in advanced propulsion technologies aimed at reducing travel times for Mars missions. However, the unique electromagnetic acceleration capabilities of the Russian plasma engine set it apart from existing methods, potentially offering a competitive edge in the race for interplanetary travel. 7. Expert insights. Alexei Voronov, a prominent figure in the project, emphasized the significance of the plasma engine's ability to accelerate charged particles. He noted that this represents a substantial leap in propulsion technology, enabling speeds far exceeding the limitations of traditional engines, which max out at about 4.5 km per second due to combustion constraints. In summary, Rosatom's development of a plasma electric rocket engine signifies a promising step toward achieving faster Mars missions while enhancing the safety and efficiency of interplanetary travel. As testing progresses and the functional flight model is expected by 2030, this technology could redefine humanity's approach to space exploration, potentially ushering in a new era of interplanetary travel. References. 1. World Nuclear News / www.worldnuclearnews.org/articles/Mars in 30 days, Russia unveils prototype of plasma rocket engine. 2. Interesting engineering. //interestingengineering.com/space/Russia plasma engine could reach Mars early. 3. Deccan Herald //www.deccanherald.com/science/space/Russian scientists develop space propulsion system that could reach Mars within 1-2 months. 3398373. The announcement by Rosatom regarding the development of a plasma electric rocket engine is indeed a significant leap in space propulsion technology, particularly with its potential to reduce travel time to Mars to as little as 30 to 60 days. Here are some counterintuitive points derived from the information provided. 1. Speed versus traditional engines. While it might seem intuitive that a faster journey to Mars would require a more powerful engine, the plasma electric rocket engine operates fundamentally differently than traditional combustion engines. Traditional engines max out at about 4.5 kilometers per second due to the limitations of fuel combustion. In contrast, the plasma engine accelerates charged particles using electromagnetic fields, enabling it to reach speeds of 100 km per second, approximately 62 miles per second. This suggests that advancements in propulsion technology can lead to significant increases in speed without necessarily requiring proportionally larger or more complex engines. 2. Safety implications. It may appear that longer missions would be safer due to familiarity and preparation for astronauts. However, the opposite is true in this case. Shorter missions reduce the risks associated with prolonged exposure to cosmic radiation. This counterintuitive notion highlights that the duration of space travel can significantly impact astronaut health, underscoring the importance of propulsion technology that can minimize travel time. 3. Hybrid launch mechanism. The reliance on traditional chemical rockets for the initial launch, followed by the use of the advanced plasma engine in space, is a surprising combination. One might assume that a novel propulsion technology would fully replace older methods. However, the current hybrid approach allows for the immediate benefits of advanced propulsion while still leveraging established technologies for initial launch phases, demonstrating a pragmatic step towards innovation. 4. Fuel usage. The plasma engine uses hydrogen and operates by accelerating charged particles, which may seem less efficient compared to traditional fuels. However, the engine does not require large quantities of fuel to operate once in space, as it carries only a small amount of gas for acceleration. This suggests that the plasma engine could be more efficient in the long term for interplanetary travel, where the mass of fuel could significantly impact the spacecraft's launch and travel capabilities. 5. Potential for beyond Mars. The implication that this engine could enable travel beyond the solar system may seem overly ambitious. However, the technology's ability to achieve higher speeds and reduce travel times could make such distant missions more feasible than previously thought. This challenges conventional wisdom about the limitations of current propulsion technology regarding deep space exploration. 6. Lack of peer review. While the claims surrounding the plasma engine are promising, the absence of peer-reviewed scientific publications or technical documentation raises questions. Given the monumental implications of this technology, one might expect that such innovations would undergo rigorous scrutiny. The current state of the technology's validation might be surprising to those accustomed to a more formal scientific process. 7. Research and development timeline. The expectation of a flight-ready model by 2030 may seem optimistic given the complexities involved in developing new propulsion technologies. Yet it reflects a growing trend in space exploration where rapid advancements and iterative testing are prioritized to meet ambitious exploration goals, contrasting with more traditional, slower-paced development cycles. These counterintuitive insights highlight the innovative aspects of Rosatom's plasma electric rocket engine and its potential impact on future space travel, illustrating how advancements can challenge existing paradigms and expectations in aerospace technology. Overlooked aspects of Rosatom's plasma electric rocket engine development. The announcement by Rosatom regarding the development of a plasma electric rocket engine capable of significantly reducing travel time to Mars has generated considerable excitement. However, several critical aspects of this development are likely to be overlooked by the general public and even some experts in the field. Understanding these nuances is essential for grasping the full significance of this breakthrough in space propulsion technology. 1. Impact on cosmic radiation exposure. While many reports highlight the reduced travel time as a primary benefit of the new plasma engine, the implications for astronaut safety due to reduced cosmic radiation exposure are often underemphasized. Traditional missions to Mars, which can take nearly a year, expose astronauts to considerable levels of cosmic radiation. This includes high-energy particles from solar flares and cosmic rays that can increase cancer risk and cause other health issues. By shortening the duration of the journey to just 30 to 60 days, the new plasma engine could drastically lower the cumulative radiation dose received by astronauts. This is particularly significant as space agencies consider long-duration missions not just to Mars but potentially to other destinations, including the outer planets or beyond the solar system. The health implications of long-term exposure to radiation are still being studied, but reducing time in space could be a game-changer in ensuring astronaut safety on future missions. 2. Technological scalability and adaptability. Another aspect that may be overlooked is the scalability and adaptability of the plasma propulsion system. The architecture of the plasma electric rocket engine, which uses a magnetic plasma accelerator, suggests that it could be scaled for various mission profiles. This means it could potentially be used not just for crewed missions to Mars but also for robotic missions, cargo transport, and even interstellar probes. The hybrid approach, using chemical rockets for initial launch and plasma propulsion for space travel, could serve as a model for future spacecraft designs. This adaptability means that the technology could find applications across a range of missions, broadening its impact and utility in space exploration. 3. Economic and logistical considerations. The cost and logistics of producing and deploying this new engine technology are significant factors that are often glossed over. While the technical specifications and capabilities of the plasma engine are impressive, the economic feasibility of developing such advanced propulsion systems is crucial for long-term space exploration plans. The projected timeline for a flight-ready model by 2030 raises questions about funding, resource allocation, and international collaboration. The production costs, potential partnerships, and the integration of this technology into existing spacecraft designs all require careful consideration. Overlooking these economic factors could lead to unrealistic expectations about the rapid deployment of this technology in upcoming missions. 4. Comparison with other propulsion technologies. While the Rosatom plasma engine is touted for its unique capabilities, it is essential to contextualize this development within the broader landscape of emerging propulsion technologies. Various international efforts are underway to innovate in space propulsion, including nuclear thermal propulsion, solar sails, and other electric propulsion systems. Understanding how Rosatom's plasma engine compares to these technologies in terms of efficiency, speed, cost, and safety is crucial for evaluating its potential impact on future missions. Dismissing the competition might lead to an underestimation of the challenges and limitations faced by this new technology. 5. A public perception and international collaboration. The perception of technological advancements often influences public support for space exploration initiatives. The narrative that emerges from the successful development of the plasma engine could impact funding and political support for broader space missions. Moreover, international collaboration in space exploration is becoming increasingly vital, as no single nation can undertake ambitious missions alone. The implications of Rosatom's development extend beyond Russia, how this technology is shared, or whether it leads to partnerships with other spacefaring nations, will shape future exploration efforts. A failure to recognize these diplomatic and collaborative dimensions could hinder the advancement of space missions that rely on collective expertise and resources. Conclusion. The unveiling of Rosatom's plasma electric rocket engine is a pivotal moment in the field of space propulsion technology. However, the significance of this development extends far beyond the immediate technical specifications and potential travel time reductions. Understanding the implications for astronaut safety, technological scalability, economic feasibility, competitive landscape, and international collaboration are essential for grasping the full context of this advancement. These overlooked aspects could ultimately influence the trajectory of human exploration in space, shaping not only missions to Mars but also the future of interplanetary and potentially interstellar travel. 1. Technological innovation. The Rosatom plasma electric rocket engine signifies a major leap in space propulsion technology. Utilizing a magnetic plasma accelerator, this engine can accelerate charged particles, electrons and protons to speeds of 100 km per second, far surpassing the maximum speed of traditional chemical rocket engines, which is limited to around 4.5 km per second due to combustion constraints. This innovation not only allows for significantly faster travel times to Mars, estimated at just 30 to 60 days, but also paves the way for future interplanetary explorations and potentially missions beyond our solar system. 2. Safety enhancements. One of the critical advantages of this new propulsion system is its potential to enhance astronaut safety. Traditional missions to Mars can take nearly a year, exposing astronauts to prolonged cosmic radiation, which poses serious health risks. By reducing the travel time to as little as 1 to 2 months, the plasma engine could significantly minimize these risks, making manned missions to Mars and beyond more feasible and safer. 3. Testing and development timeline. The development of the plasma engine is in its early stages, with a prototype currently being tested in a specialized vacuum chamber to simulate space conditions. A flight-ready model is expected to be available by 2030 following extensive ground testing. This timeline is crucial for the aerospace community as it marks a significant milestone towards operational deployment of advanced propulsion technologies that could redefine space exploration. 4. Hybrid launch mechanism. While the plasma engine represents an advanced propulsion technology, the initial launch into orbit will still rely on traditional chemical rockets. This hybrid approach allows for a gradual transition from Earth to space, where the plasma engine can take over for deeper space missions. This strategy highlights the practical integration of innovative technologies with existing methodologies, ensuring a smoother operational process in space travel. These 4 points emphasize not only the technological advancements represented by Rosatom's plasma electric rocket engine, but also the broader implications for astronaut safety, the timeline for development, and the integration of new propulsion methods with established launch techniques. 1. The V-2 rocket. Germany. World War II. The V-2 rocket, developed by German engineer Wernher von Braun during World War II, was the world's first long-range guided ballistic missile. It marked a significant advancement in rocket technology and laid the groundwork for future space exploration. The V-2 could reach altitudes of 189 kilometers (118 miles) and travel at speeds over 5,700 kilometers per hour (3,600 miles per hour). Its development was pivotal in demonstrating the potential of rocket technology for both military and civilian applications. After the war, many of the scientists involved in the V-2 program were brought to the United States as part of Operation Paperclip, significantly influencing the U.S. space program. 2. NASA's Space Shuttle Program. USA 1981 to 2011. The Space Shuttle program was a landmark in space travel, allowing for reusable spacecraft that could carry astronauts and cargo to and from low Earth orbit. The program facilitated numerous missions, including satellite deployment, scientific research, and assembly of the International Space Station (ISS). The shuttle's ability to return safely to Earth after missions represented a significant evolution in space travel technology, making it more accessible and cost-effective for scientific exploration. The program's legacy continues to influence modern space travel and exploration strategies. 3. Project Orion. USA 1950s to 1960s. Project Orion was a concept for a spacecraft intended to be propelled by nuclear pulse propulsion. The idea was to use nuclear explosions to push the spacecraft forward, theoretically allowing for faster travel within our solar system. While the project was ultimately abandoned due to nuclear test ban treaties and safety concerns, it demonstrated the potential for advanced propulsion technologies that could revolutionize interplanetary travel. The concepts explored in Project Orion continue to inspire modern discussions about propulsion systems capable of reaching distant planets like Mars in significantly reduced timeframes. Future outlook: Rosatom's plasma electric rocket engine and the next era of space travel. The recent development of Rosatom's plasma electric rocket engine represents a pivotal moment in space exploration technology. By drastically reducing travel times to Mars to just 30 to 60 days, this innovative propulsion system could reshape our understanding of interplanetary travel and exploration. Here, we explore the potential future implications of this breakthrough technology. 1. Rapid interplanetary travel. A major advantage of the plasma electric rocket engine is its ability to significantly shorten travel times not only to Mars but potentially to other celestial bodies as well. With advancements in propulsion technology, missions to destinations like the moons of Jupiter or Saturn could become feasible within a few months rather than years. This rapid travel time could enable more frequent missions, leading to a more extensive exploration of our solar system. 2. Enhanced astronaut safety. The shorter duration of space missions will reduce astronauts' exposure to harmful cosmic radiation and other risks associated with prolonged space travel. As the plasma engine allows for quicker journeys, it may improve the health and safety of crew members, making long-term missions to Mars or beyond more viable. This could facilitate the establishment of human habitats on other planets, a goal that has been ambitious until now. 3. Economic and logistical implications. As space missions become faster and more efficient, the economic landscape of space travel could change dramatically. The reduced travel times may lower the costs associated with prolonged missions, such as life support, food, and supplies. This could open the door for commercial space travel and tourism, making space more accessible to private enterprises and individuals. 4. Technological advancements and collaborations. The development of the plasma electric rocket engine could stimulate further technological advancements in propulsion systems. Other countries and private companies may be inspired to accelerate their own research and development efforts in advanced propulsion technologies. This competitive environment could foster international collaborations, leading to more innovative solutions for space exploration challenges. 5. Interstellar exploration. While the immediate focus is on Mars and the inner solar system, the capabilities of the plasma electric rocket engine might eventually extend beyond our solar system. If successful, the technology could make interstellar missions more feasible, potentially allowing humanity to explore exoplanets and other star systems within a reasonable time frame. This could significantly expand our understanding of the universe and our place within it. 6. Hybrid launch systems. The reliance on traditional chemical rockets for initial launch while utilizing the plasma engine for deep space travel introduces a hybrid approach to space travel. This method can leverage the strengths of both propulsion technologies, ensuring that spacecraft can reach orbit efficiently while still benefiting from the advanced capabilities of plasma propulsion during longer journeys. 7. Environmental considerations. As space exploration continues to expand, the environmental impact of space travel will become increasingly important. The plasma electric rocket engine, which relies on hydrogen and generates thrust through electromagnetic fields, may offer a cleaner alternative to traditional propulsion methods. This could lead to a new era of environmentally responsible space exploration that takes into account the ecological footprint of human activities beyond Earth. 8. Impact on scientific research. The quicker travel times afforded by the plasma engine could facilitate more frequent scientific missions to Mars and other celestial bodies. This might lead to a more dynamic approach to planetary science, allowing for real-time experimentation and observation, ultimately enhancing our understanding of planetary geology, atmospheres, and potential for life. 9. Public interest and engagement. The excitement surrounding faster travel to Mars could reignite public interest in space exploration. As missions become more frequent and accessible, this could inspire a new generation of scientists, engineers, and enthusiasts. Increased public engagement may also lead to greater investment in space programs, both from governmental and private sectors. 10. Timeline for implementation. The timeline for the practical implementation of Rosatom's plasma rocket engine is projected to culminate in a flight-ready model by 2030. As extensive ground testing is conducted, we can expect incremental milestones that will validate the technology, laying the groundwork for operational capabilities. By the 2030s, the implications of this technology could begin to materialize, ushering in a new era of human spaceflight. Conclusion. In summary, the successful development and implementation of Rosatom's plasma electric rocket engine hold the promise of revolutionizing space travel. With potential benefits ranging from enhanced astronaut safety and faster interplanetary missions to economic opportunities and environmental sustainability, this technology could redefine humanity's relationship with space. As we move toward a future where interplanetary travel becomes routine, the dreams of exploration beyond our home planet may finally become a reality.